Welcome, everyone. Today, we are going to open the black box of vision transformers. We'll be taking an interactive, end-to-end walkthrough of the ViT inference pipeline to see exactly how a model looks at an image of a dog and turns it into a final prediction. But first, why is this difficult? The truth is, spatial dynamics make vision interpretability uniquely challenging. In natural language processing, data is sequential and readable. A sentence like "the dog sits" maps neatly into 1D tokens. Vision, however, requires complex 2D mapping. We face a spatial mapping problem where attention has to map to 2D image regions, not just a sequence of words. Furthermore, we run into a decoding problem, as intermediate layers decode into abstract class labels rather than easily readable text. Because of this complexity, existing tools leave a critical gap in end-to-end visual understanding. While we have great tools like ViT-Explainer for convolutional networks, or ViT-Explainer for text, they don't cover the full picture for vision. That is exactly the gap ViT-Explainer fills, providing vision modality support, an end-to-end walkthrough, patch-level spatial overlays, and layer-wise Logit lenses all in one place. ViT-Explainer serves as a unified interactive environment that connects image tokenization directly to the final classification. It's designed for students, educators, and researchers. The front end is fully browser-based using Svelte, while the back end is powered by PyTorch and the TIM library. Under the hood, it runs a pre-trained FlexiViT large backbone with 24 layers and 16 attention heads. We specifically built a pedagogical architecture, optimizing for human comprehension rather than raw scale. A standard ViT configuration has so many patches that individual weights get lost, requiring endless scrolling and aggregation. By adapting the model to use a simplified 3x3 grid, users can inspect every individual attention weight simultaneously right in the browser, transforming a black box into a clear pedagogical tool. Let's walk through the pipeline. Phase 1 is translating pixels into a sequential format. Remember, the model does not actually see a picture, it processes flattened RGB patch vectors. We start with patch extraction, move into channel decomposition for red, green, and blue, and finally flatten these into a 1D sequence of vectors. In Phase 2, we are embedding the sequence and restoring spatial awareness. We take those flattened patch vectors and multiply them by a learned weight matrix to project them into the embedding space. Here, we add a dedicated CLS token used for final classification, and we inject positional encodings to retain the 2D spatial origin of each patch so the model doesn't lose track of geometry. Moving into Phase 3, we deconstruct the transformer encoder block. We visualize the architecture step by step without skipping any intermediate operations. You can see the data flow through layer normalization, into the multi-head attention mechanism, and pass through the MLP sublayer, complete with residual connections. Let's take a deep dive into that attention mechanism. Here, we unpack the multi-head self-attention dynamics. We reveal exactly how parallel heads redistribute token information row by row. You can watch queries and keys multiply to form scaled similarities, which pass through a softmax function to generate the final attention weights for all 16 heads. But numbers alone aren't enough. We map these mathematical weights directly to spatial realities. Using the interface's sidebar, you can select any layer and any head, and watch the attention focus project back onto the original image of the dog. This allows you to visually inspect exactly where the model is looking. Finally, in Phase 4, we trace prediction evolution using the Vision Logit Lens. By applying the classification head to the CLS token at every single intermediate layer, you can watch the predictions sharpen in real time. As semantic meaning is progressively encoded deeper into the network, you can see the Logit scores for Golden Retriever or Cocker Spaniel rise to the top. To support different types of users, the tool features dual interaction modes based on the principle of overview first, details on demand. We offer a guided mode, which is a synchronized, step-by-step walkthrough ideal for building an initial mental model. We also offer a free exploration mode, giving users unrestricted interaction to upload custom images, inspect arbitrary heads, and test edge cases. We put this system to the test. Our empirical validation proved high usability and low cognitive load. In user evaluations, the tool scored an excellent 90.42 out of 100 on the system usability scale. Users also reported very low overall workload and frustration levels when navigating these complex topics. Ultimately, the tool succeeds in transforming abstract operations into concrete mental models. Qualitative feedback directly mapped to our interface features. Users stated that the spatial overlays helped them see how attention heads distribute focus, the explicit QKV breakdown made the pipeline's logic clear, and the Logit Lens made the network's depth actually make sense. Looking ahead, we are expanding the framework for future interpretability. We invite you to experience the glass box yourself via our live demo. In our future work, we plan to implement refined affordances for clearer visual cues, add back-end support for standardized 14 by 14 or 16 by 16 grids, and expand beyond classification into detection and multimodal architectures. Thank you for watching.